4.3, Logarithmic Functions. So what we're going to look at now are the opposite of exponential functions, which we were just looking at, or the inverse of exponential functions. So when we're talking about log functions, if we take y as being a real number and a and x as being positive numbers, where a is not equal to 1, then we can say that y is equal to the log base a of x is equivalent to x is equal to a to the y. Where this is the same x, that's the same a, and that's the same y. And we call this y equal to log base a of x, known as base a. X is equal to a to the y, where a is the base and y is the exponent. So those are equivalent statements, which means that we can take an equation involving a logarithm and we can write it as an equation involving an exponential, or we can take an equation involving an exponential and rewrite it as an equation involving a logarithm. And as I said, these are inverse functions. Notice that if you take log base a raised to the, log base a of x, it gives you y. If you take a raised to the y, it gives you x. So they're reversing. So actually, I'm going to leave that up there, and we're going to fill in a table. So we're going to put log form over here, exponential form over here, and let's start with log base 1/2 of 8 is equal to -3. Over here we're going to give 3 to the 4th is equal to 81. Over here log base 5 of 1 over 125 is equal to, -3. Over here, 10 cubed is equal to 1,000. Log base 6 of 1 is equal to 0. And 12 to the 1 is equal to 12. So now we have these. This is our starting functions. We want to convert those to the opposite form. So if we have log base 1/2 of 8 is equal to -3, according to this equivalency, that means we can take that base 1/2, raise it to this power, and set it equal to that. So notice we have a log base a, where a is 1/2, a to the y, a is 1/2, y is equal to, that's the -3, a raised to the y, -3, of 8, x is 8. So that's all we're doing. Come over here, we have a to the y is equal to x. So log base a of x is equal to y. So 5 to the -30 is equal to 1 over 125. Log base 10 1000 is equal to 3. 6 to the 0 is equal to 1. Log base 12 of 12 is equal to 1. So just converting back and forth between log form and exponential form. Now you may look at this and go, well, why would I want to do that? Who cares? Well, the reason we want to be able to do this is because it can actually allow us to solve things that otherwise we would not be able to solve. Because if we can change it back and forth, we can get a variable over to where it's easily solvable. If we look at 1/2 to the negative 3, if this was a variable we were looking for, 1/2 to the x, then we may have some difficulty. Whereas this would tell us, oh, well, we take log base 1/2 of 8, and we can solve for x. So it can be a way that we can manipulate the expression or equation to be able to solve for one of the variables. So let's get our example table here out of the way. Okay, so having that, now a logarithmic equation, I'm going to say an equation with a logarithm in at least one term. Many logarithmic equations can be solved by first writing the equation in exponential form. Right, so let's look at some examples of that. I'm going to use my red marker because that's what's working well. Log base x of 16/9 is equal to -2. Now, if we look at this, we're looking at x's in the base here. How are we going to solve for that base? Well, if we convert it to an exponential function, that's x to the -2 is equal to 16/9. So 1 over x squared is equal to 16/9. Well, 16/9 is 4/3 squared. So we could put this as 1 over x squared is equal to 4/3 squared. So 1 over x is equal to 4/3, or x is equal to 3/4. Because we were able to take it from a logarithmic form and put it in exponential form. Well, let's do another one. Log base 16 of x is equal to 3/4. Well, let's convert it to exponential form. So that's 16 to the 3/4 is equal to x. Well, obviously that's going to work much easier. Now, I look at this and I remember that we can either do that as 16, the 4th root of 16 cubed, or we can do it as the 4th root of 16 cubed. And in this case, I see that the 4th root of 16 will work much easier for me because I see the 4th root of 16 is 2. So I have 2 cubed. So x is equal to 8. So once we convert it to exponential form, really easy to solve. Log base 36 of radical 6 is equal to x. Okay, I don't know how to deal with log base 36, do you? Okay, so let's see what happens here. So let's turn it into an exponential. So 36 to the x is equal to radical 6. Well, I don't know if that helps you much, but if you remember what we did with exponentials, we said if we can get the same base, then the exponents must be equal to each other. So I see 36, I see 6, and I go, wait a second. I can write 36 as an exponential with a base of 6. I can say that 6 squared to the x is equal to 6 to the 1/2. Well, and actually use our power property, we made 6 to the 2x is equal to 6 to the 1/2. Well, if the base is the same, then the exponents must be equal. So 2x is equal to 1/2, or x is equal to 1/4. So you see how this can actually make it much easier to work with. And that's why we want to know that equivalency. Okay. So let's look at the logarithmic function. Logarithmic function, if we have a greater than 0 and a not equal to 1, remember those are the rules, and in this case we're going to say x greater than 0. The reason we say this is because you can't take the logarithm of a negative value. Sorry, just the way it is. Then f of x equal to log base a of x is a logarithmic function. Now let's remember that the logarithmic function and exponential function are inverses of one another. And that's going to become very important as we talk about graphing and what they actually look like. Remember what happens when you have inverses. The x and y values, or the inputs and outputs, flip. So now if we think back to graphing exponential functions, we should readily know that there are 3 points that will occur on the graph of a logarithmic function. And remember, when you change x and y, we also said when graphing that the inverse of a function was the function reflected over the line y equal to x. So that's going to give us the other thing. So we remember that with an exponential function, we had the point -1, 1 over a. Well, for a logarithmic function, we have the point 1 over a, sorry, not a, 8a, -1. For exponential function, we have the point 0, 1. For logarithmic function, we have the point 1, 0. And then for an exponential function, we had 1a. So for a logarithmic function, we have a1. And with the thought of the flipping or reflecting over the line y equal to x, we should also recognize that we had an asymptote for exponentials that was the x-axis. Well, if we flip that over the line y equal to x, that means that the y-axis becomes an asymptote. So we have the necessary information to be able to start graphing this. And realize also that the domain and range will now change. So the domain, if you remember for exponential functions, the domain was all real numbers, and the range was from 0 exclusive to infinity. So now here, the domain will be from 0 to infinity, and the range will be from -infinity to infinity, all real numbers. Okay, the other thing I want to mention is, and this follows along as it did for exponential functions, if a is greater than 1, then it is increasing, and if a is between 0 and 1, then we are decreasing. So all the things we need to know to be able to graph a logarithmic function. So now I'm going to get all this information out of the way. Luckily with videos, you can always go back and look at it. And if we were in person, we would have much bigger boards to work on, so I'd be able to put it off to the side. Okay, so let's look at some possibilities here. F of x is equal to log base 1/3 of x. So we know we can find 3 points. And if it helps, you can do them in reverse. -1 for the y value, and then the reciprocal of this, 1 over a, will be the x value, so that would be 3. Reciprocal of 1/3 is 3. For y equal to 0, x is equal to 1. So for y equal to 1, x is equal to a, or 1/3. And we know the y-axis is the asymptote. So there we go. Let's plot it. Always number your axes. Go back and count how many times I've said that, okay? Always number your axes. So we can plot these points. We know that the y-axis is going to be an asymptote. So we have 3, -1, 3, -1, 1, 0, and 1/3, 1. And it's going to approach the y-axis but never touch it, and continue getting further and further away from the x-axis, so it's going to go to infinity. So we can see that the domain is from 0 exclusive to infinity, and the range is from -infinity to positive infinity, all real numbers. Well, let's do another example, but let's throw in some transformations, because we really can do all of the normal things, and then throwing in transformations just allows us to accomplish a little more as we do it. So let's do f of x is equal to log base 2 of x minus 3 plus 2. So f of x is equal to log base 2 of x minus 3 plus 2. So let's start it out as we did in the past, like when we did the exponents, and get our 3 points from log base 2 of x, because that's the main function. So we're going to call the base function log base 2 of x is going to be 1 over a, so 1 over 2, -1, 1, 0, and a, 2, 1. So we have our 3 points. Next thing that happens is x minus 3, that's a shift to the right by 3. So that means our x values are going to do it. So we're going to shift right by 3. So our x values are going to move over 3 to the right, so that gives us 3.5, negative 1, 4, 0, and 5, 1. Then what do we have plus 2. So it's going to shift up by 2. So our y values are going to increase by 2. 3.5, 1, 4, 2, 5, 3. Now the other thing we have to take into account is the asymptote. Our asymptote was the y-axis. So vertical is not going to do anything, it's the horizontal. So we had a horizontal shift to the right by 3. So x equal to 3 will now be our asymptote. So x equal to 3 becomes our asymptote. Well, let's graph it. We've got that. I'm going to do what I did last time, is I filled in all that space, so I moved this out of the way, so we can use as much of the board as possible. Okay, so I've numbered my axes, so I'm ready to put this on here. So 3.5, 1. 3.5, 1. 4, 2. 4, 2. 5, 3. 5, 3. And we have an asymptote at x equal to 3. So again, draw it in. Because with the sloppiness of my drawing on here, it could be confusing. We may want to treat it as an exponential growth. It's not an exponential growth, and if you look carefully, you can see that that is not straight. I'm just going to use this little thing here, and we can see that it is definitely curving. Notice how that made that other one disappear. It is most definitely curving, but it can be very easy to mistakenly think that it's not. So there we go. So it's going to come through here, and it's going to have that asymptote there. You continue on that other way, and we have f of x equal to log base 2 of x minus 3 plus 2. So graphing it. Personally, I think it's kind of cool that you can graph exponential functions and logarithmic functions so readily, that there are those 3 points that you can easily determine. And all you really need to do to be able to determine those is recognize the very basic properties of exponentials, that any number raised to the negative 1 is just its reciprocal, any number raised to the 0 is 1, and any number raised to the first power is itself, and then realize that logarithmic functions are just the inverse. So therefore, flip them. So you're going to be able to, you can come up with those 3 points really easily, and then just remember exponential functions have an asymptote at the x-axis unless there is a vertical shift, in which case they will shift however much. And for logarithmic functions has an asymptote at the y-axis unless there's a horizontal shift, and then it will shift that much. So it makes it easy for us to continue through. Okay, so now we're going to talk about some properties of logarithms. Because we've talked about the properties of exponents, and actually we've been able to just kind of jump over that a little bit because we've talked about that numerous times before. So for an exponential function, we just had all of those properties carry through. For logarithms, this is something a little new for most of us. We may not be familiar with them. So here are some properties of logarithms. Now remember that in this case, we're dealing with x greater than 0, y greater than 0, a greater than 0, and a not equal to 1. And we're going to say r is any real number. Okay. So our property is the product property. If you have log base a of x times y, that can be rewritten as log base a of x plus log base a of y. So if you have log base a of a product, that can be written as the sum of log base a of each of those factors. The quotient property. If you have log base a of x over y, that is the equivalent of log base a of x minus log base a of y. So if you have the log of a quotient, that can be written as the difference of the log of each of the pieces of that, the divisor and the dividend. The power property. Log base a of x to the r can be rewritten as r times log base a of x. So if you have a log of something raised to a power, that power can be pulled out and multiplied by the log without that power. Without any name for it, just logarithm of 1, log base a of 1 is equal to 0. Remember that it's the inverse of an exponential. A to any number raised to the 0th power is 1. So log base a of 1 is equal to 0. And log base a of a is equal to 1. Any number raised to the power of 1 gives you that number back. So log base a of a is equal to 1. And remember, these two properties just come from the definition that we gave initially, that log base a of x is equal to y is equivalent to a to the y is equal to x. So we can see those directly from that. So let's use these to do some rewriting of logarithms. Log base 7 of 8 times 6. We want to rewrite this logarithm using some of our logarithmic properties. Now I know you're looking at this and going, well, why can't I just multiply 8 times 6 and get 48 and then say log base 7 of 48? Well, maybe you can. The reason that this becomes important is because sometimes we know what the log of something is. So if we can rewrite an expression in terms of that, then we can use that log we already know as opposed to having to calculate it. Or other times, we may be able to pull part of it out. So we may be able to, like we know that log base A of A is equal to 1. Well, what if this was log base 7 of 7 times 6? Well, now I can split it out and get a log base 7 of 7. Well, that's equal to 1 plus log base 7 of 6. So that's why it's important to be able to do this. So when you're asked to do it, don't just multiply it together and say, see, I rewrote it. There are reasons for doing this. So log base 7 of 8 plus log base 7 of 6. Try another one. Log base 6 of 12/5. Well, that's the quotient rule. So that's log base 6 of 12 minus log base 6 of 5. Log base 2 of the cubed root of 9. You may look at this and go, well, wait a second. Well, cubed root, remember, that's just a rational exponent, isn't it? So that's just this raised to the 1/3. So I can say that's equivalent of log base 2 of 9 to the 1/3. And if we have a power, we can pull that out front, is equal to 1/3 log base 2 of 9. Now let's get fun here. Log base b of rs squared t over u cubed v to the 5th. And you go, wow, Mr. Davis talking about jumping out of nowhere, right? So here we go. So this is tying all this together, and there are a few ways we can work through this. I'm going to start by breaking it into pieces and saying, okay, well, first of all, I see a quotient here. So I can rewrite this as log base b of rs squared t minus log base b of u cubed v to the 5th. I can start out with that. And then I can say, well, now I have products. So I can say this is log base b of r plus log base b of s squared plus log base b of t minus whatever the rest of this is. So I am going to point out with this that if we minus these, remember that's a product, so we can come up with an addition, but I'm going to be distributing through this negative anyway, so I can say that's minus log base b of u cubed minus log base b of v to the 5th. If you don't like that, then I can write it like that, right? We're going to subtract this, which is that sum. From there, I can now simplify any exponents. So I have, and distribute that negative sign. Log base b of r plus 2 log base b of s plus log base b of t minus 3 log base b of u minus 5 log base b of v. And so now I've turned it into this long expression here. Now I will point out that we could have done this a little bit faster if we just realized that because of the distribution that happens of that negative sign, anything in the numerator is going to be added, anything in the denominator is going to be subtracted. If we have a power, it's going to come out front. So we can just read this as log base b of r plus 2 times the log base b of s plus log base b of t minus 3 times log base b of u minus 5 times the log base b of v. You see, we can just pull it all out of that one setup there. Now, since we can do that, we can also go the other direction. We can start with something that is in this form, and I just lost my eraser. There we go. So we can start with something that's in the form of sums and differences of logs. And remember, this will only work if they have the same base, but we can group them into one big thing. So let's say log, I'm not going to use that marker. Let's see if the black one will work for me. So log base 4 of x minus log base 4 of y plus log base 4 of z. Now remember what I just said about we can, if it's in the numerator, we add it. If it's in the denominator, we subtract it. Well, then we can pull this right from here. We can rewrite this as log base 4 of, well, that's plus, so xz over y, because the y was being subtracted. How about 4 log base b of r minus 5 log base b of s? Well, now again, if it's positive, if it's being added, it's in the numerator. If it's being subtracted, it's in the denominator. And if we have a coefficient, if it's multiplied by some constant, that becomes a power. So we're just reversing the process. So this becomes log base b of r to the 4th over s to the 5th. And how about 1/3 log base a of x plus 2/3 log base a of y minus log base a of xy? I'm just going to write that below to give myself a little more space, but we have log base a and we have plus, plus, minus, so x to the 1/3, x to the 1/3, y to the 2/3, over xy, and then we can rewrite that in the form of radicals if we want. Will give us log base a of the cubed root of x times the cubed root of y squared over xy. And now I see a cubed root and a cubed root, so I can combine them, and I can say log base a of the cubed root of x y squared over x y. So we can take it from this into one succinct logarithmic function as long as the bases are the same. Remember, none of these rules can be used if the bases are not the same. Okay, so let's apply some of this and say that we have this information. Log base 10 of 3 is equal to 0.4771. And I want to find log base 10 of 9. Well, how are we going to do that? Log base 10 of 9. We know that log base 10 of 3 is 0.4771. Well, what we can do is we're looking to get things in terms of log base 10 of 3. So look at this, we go, oh, well, isn't that log base 10 of 3 squared? And if we have a power, can't we bring it out front? Is equal to 2 log base 10 of 3. And then we know what log base 10 of 3 is equal to 2 times 0.4771, which is equal to 0.9542. So we knew log base 10 of 3 was 0.771, and we were able to use that to find log base 10 of 9 by using some of the things that we had. Let's try another one. Again, knowing that log base 10 of 3 is 0.4771, log base 10 of 20 over 6. Well, look now and go, well, what can we do with this? Well, first of all, I see that 20 over 6 can be reduced. So I can say that's log base 10 of, well, if I divide it by 2, I get 10/3. Alright, so that's a start. And then I go, well, wait a second, that's a quotient. So that's the same as log base 10 of 10 minus log base 10 of 3. Oh wait, log base 10 of 10, if we have a log base a to the a, that is 1. So that's equal to 1. And then log base 10 of 3, we know is 0.4771. So therefore log base 10 of 20 over 6 is equal to 0.5229. Again, because we knew this, we're able to come from this and calculate it. Okay? So last thing we want to cover on these logarithmic functions is the theorem of inverses. Theorem of inverses basically says that if you have a to the log base a of x, that is equal to x, and that if you have log base a of a to the x that is equal to x. Well, if you think about it, remember when we were dealing with inverses, we said the composition, right? If you take f of g of x, and that's equal to x, and g of f of x, and that's equal to x, then you have inverses. So this is taking the exponential of the logarithm of a dx, gives you x, and then the logarithm of a to the x gives you x. So that's just the composition and saying that it works for logarithmic functions and exponential functions. So basically, what that allows us to do, and let me just switch back to my red marker for this last thing, is if I have 6 log base 5 of 5, well, can't that be written as log base 5 of 5 to the 6? And this tells me if I have log base a of a to the x, that this is going to be equal to x. That's going to be equal to 6. And if I have log base 3 of 3 to the 7, log base a of a to the x is equal to x, which in this case is 7. And there we go. That is section 4.3, logarithmic functions.